Okay, so you notice that this chapter is a little mathy, but it's the simplest way to treat nonlinear optics, actually. And I think what I want you to remember, hopefully, is what nonlinear effects give rise to, what kind of phenomena you expect from a nonlinear crystal, and maybe the idea of how to start to calculate things. Because the idea is not that hard. It's really a mechanics problem. Okay? So basically the nonlinear effect arises when we have a force that is no longer linear in displacement. So this is the displacement of an electron. This is the acceleration term. This is the loss. Now we know it's the collision term. So that's how the charge dissipates energy. This is the restoring force, because the charge is connected to the nucleus. Okay, so this is the dielectric component. This is the metal component, the conductor component, in a way, right? And then on the right-hand side is the driving force. This is capital E is the electric force that is charge. It's displacing the charge, the electron, and the electron tends to follow that electric field. Nonlinearities happen when this driving field is so hard that there is another force here that depends nonlinearly on x. And I gave you an intuitive picture for what happens if you have, this is exactly the problem of mass on a spring, same equation. So if you stretch your spring too much, so you apply too much force, you drive it too hard, at some point you may find that the elastic constant of the spring depends on how much input you put on. That's the spirit of nonlinearity, the fact that the property of the material depends on your input. Right? For linear systems, that never happens. You have the impulse response that is always constant, right? With the input. No matter what the input is, the impulse response stays the same. So that's what we've been doing the whole class. The impulse response, point spread function of your microscope, all these, they're always constant with respect to your input. Nonlinearity means that the material response depends on your input. So that's what happens when you stretch a spring too much. The elastic constant can get both ways, can be higher or lower. So you could get stiffer or more or less stiff. So this, in the case of an electron revolving around nucleus, what we found is that actually that nonlinear component appears when you have a curvature in the trajectory, which essentially means that the Lorentz force now is no longer negligible. Okay, because the Lorentz force is that cross product between H and V. When the motion is linear, you get Lorentz force that is exactly zero. The moment you have some curvature, that force is not negligible. And we were even able to calculate kind of an order of magnitude power for when that happens, okay? So this is the component that we neglected in all linear optics when we put the driving force as the electron charge times electric field. We essentially neglected the second part of the electromagnetic force, which is the magnetic one, right? The Lorentz force. Okay, so we had fun writing here the cross product. Confused ourselves, but basically if you write that equation from above on the three components, clearly you have here an extra force that depends, if I assume my electric field is along x and the magnetic field, so I have a plane wave, electric field is along x, let's say this is x, then magnetic field will be along y and I'm propagating along z. Yeah? Then these are the only components that survive. Okay? So the z component of the velocity and the y component of h, and the x component of the velocity and the same component of h. H is fixed. Yeah? So nothing happens on y. Why is that? So this is the electric field x, this is h, y, I propagate along z. Why nothing happens on y? I mean, if something happens, the linear thing happens. Right, because that is the direction of the magnetic field. So the Lorentz force cannot exist parallel to the magnetic field, right? It's a cross product. Good. Okay, so how do we solve these differential equations? Again, these are just equations of motions on 3 components. What do we do? What have we all learned and used many times in this class? It's best to bring them in the frequency domain. These differential operators, simply the equation becomes algebraic equation instead of a differential equation, right? So d at dt2 becomes minus I omega squared. This becomes I omega. This stays the same. On the right hand side, I have this derivative, and when you plug them all together, you can solve for x and z very quickly. This will be the, if I forget about this for now, this is the linear equation that we start our optical imaging class with, the ECE564. So immediately from here you can solve that x of omega is e with a minus e of omega divided by m over omega squared minus omega squared minus I omega gamma. This is the full solution of the displacement. How do we get to the refractive index? Since none of you took the ECE460, this is a microscopic quantity. This tells me, remember what x means. It means the displacement of the electron in response to my external electric field. This somehow should be able to inform me about the macroscopic properties. And in fact, we always measure macroscopic quantities like refractive index, susceptibility, things like that. So how do we go from this microscopic quantity to a macroscopic one? We calculate the p exactly. There are 2 p's actually. There is a small p, which is the induced dipole. And this is simply, basically, the charge times the displacement. And you average that. Okay? What it means is that this is the definition. It's just the dipole is the charge times the displacement. What we are going to assume, what we usually assume is that all the electrons, all the 10 to the 23 or as many as they are there, they are kind of following the same direction. So there is no spread in orientation for simplicity, right? So in that case, this average actually you can forget about it. They're all, so it just becomes a, it can stay without the averages. But now, moving to the macroscopic component, what do we do? The induced polarization this is a macroscopic quantity P will be the concentration times little p. So I'm adding them all up, basically. How many of those per unit volume I have? So this is meter minus 3. And why is this P so exciting, the induced polarization? Because this shows up in the Maxwell's equations. So what I'm trying to tell you is that solving these little mechanics equations, electron on a spring, now can teach you about the optical properties at the macroscopic scale, a measurable property of light, of the material, and essentially solve equations of propagation. It teaches you about dispersion, absorption at various frequencies, even teaches you about the plasma frequencies. Okay? So that's why solving this equation this way in the frequency domain is actually very useful. Oops, this is omega naught here, right? Remember, omega naught is the resonant frequency. Okay, so this essentially gives you a line width. Remember those profiles that we drew? The absorption looks like this, and then the refractive index looks like that, roughly speaking. Okay, so this is absorption. This is refraction. It's all coming from here. It's how this line shape looks around the resonant frequency omega naught. Okay, so what we want is the exact same thing for the nonlinear crystal. How are these shapes changing? What are the frequencies that I can have in a nonlinear crystal, okay? All right, so this was without this nonlinear term. Let's let the nonlinear term in. And what we're getting is this, that the displacement along x looks like this. So this is kind of the linear term. It's like a linear transfer function. Right? So this is like 1 over d omega. It's really like a transfer function. Why? Because I have something like x of omega output is like 1 over d omega times e of omega and some constants, right? So constant here. So this is the input. This is the transfer function. This is the output. That's the meaning of d of omega. And for the electrical engineers in the room, that's exactly the function you have for a LRC circuit. Right? So which term will be the resistor part?
The gamma.
Must be the gamma, the dissipated part, right? And LNC is the storage part, right? Make sense? Okay, so that's the meaning of this D. So I give them names so we don't carry all of them like that. And then this little b, I called it B because it has the capital B in there. It has the magnetic field in there. So then the equations look kind of like this. So if you neglect B, you get a linear response clearly, right? So if you ignore the magnetic field, you come back to the linear response. Okay? And there is nothing on Z, notice. Yeah? It means your electron follows the electric field incident on a straight line, no wobbling around, okay? You can think of it like that. All right. So we took the ratio between Z and X, and we said, what would be the power, or what would be the condition for which this aberration from linearity, so instead of moving like this, I have this kind of trajectory where I have displacement on X. What would it take to have this Z really huge comparable to the X, right? So huge nonlinearity. And it kind of came out very interesting that actually you have to deliver so much energy to the electron. So this is the energy or the work that the electron performs over a distance equal to the wavelength. That has to be comparable to mc squared, to the total energy of the electron. Isn't that kind of interesting? So you calculate the power, you end up with an amplitude, and then if you look at the radiance, this is the impedance of vacuum, you get something like 10 to the 20. Again, this is an estimate. Different materials have different constants, but it gives you an idea of how tight, how much power you have to. This is huge power. Do you know how much power we get from the sun? You don't know? You don't know. How much power do we get from the sun per square meter? How many watts per square meter do we get from the sun? For free. Every day on a sunny day. And in Arizona, every day.
15 or something.
15 watts?
Yeah, that was on
1 kilowatt. 1 kilowatt. You get 10 bulbs like that running for free from the sun for every square meter. Why do we need oil? We don't know.
Are really efficient compared to what you put compared to the sun output?
Okay, it was a rhetoric question. I know if it was cheap, we would have done it already. But I think that's the future. I mean, in the end, oil was formed also from the energy from the sun, except it took millions of years to cook it. Anyways, 1 kilowatt. So think about this. 1 kilowatt, it's a little bit less, but whatever, per meter square. So 10 powerful bulbs running continuously for every square. But look at this. The opportunity to do nonlinear optics with the lights from the sun is not that good. Although, if you look at the whole meter of it, that's a low probability. But what you can do is to take this power and squeeze it now on a micron square. Right, so let's do that and focus. Like the cruel kids burn the ants with a little lens, right? So imagine you have a meter square lens, and you focus it to a micron square. How much would that give you? Give you 10 to the 12 kilowatts per meter square. So that's 10 to the 15 watts per meter square. So it's coming closer, but still. So if you take the whole power from a 1 meter square and you squeeze it to a micron square, then you're coming close. So basically, even today with the lasers that we have, so powerful, much more powerful than what we get from the sun on this much area, rarely do you see an open or full field type of imaging technique that works on nonlinear optics. It's always focused tightly, focused down. Why? To bring this, so the same amount of power, focus it down to a small area to come close to this threshold where interesting things happen. So there are exceptions, but most of the nonlinear methods are with a focus beam for imaging confocal type geometries. All right, let's move on. I didn't review the whole idea with the first order perturbation. Where is it? I wanted to say that one more time. Okay. Okay, we'll get to it later. Okay, so what we use in the, usually with all nonlinear problems, we try to linearize them first in a way. So the intuitive picture is like this. When you stretch that spring and you change its constant, okay, that's a nonlinear problem. But if you now operate around the stretched spring, so around that new equilibrium position, if you apply new forces, you can assume it's linear around that point. You follow me? Right? So originally I had my linear spring and it's always small displacement and it's a linear problem. Now I'm putting a lot of power, the K changes, nonlinear effects for sure, but if I'm now applying small displacements around the new stretch position, I can again use the linear problem. That's what this is called the first order perturbation theory, and it's exactly what we use in the Born approximation. Remember, I wanted to stress that. So what did we say there? We said on the driving term, on the right-hand side of the equation, we had the scattered and unscattered field, and we neglected the scattered one. We said the driving term is actually due to the incident one. That's what we did in the Born approximation. Here we did the exact same thing. We said in the driving term, this is basically due to the x1, to the linear displacement. x2 can be negligible because it's much smaller. Meaning, I have this stretch, and then I have smaller stretches around the new equilibrium position. So that's a reasonable thing to do. All right. So let's look at this. We had to give up on the complex representation of the field. So we got back to a real representation. The reason is that when you start taking squares of this, you're missing on some terms. So for example, square root of u and square root of u are, square u r squared and u squared, the real part of u squared, are two different things. Okay, so, actually, so here's the perturbation. Yeah. So the goal is to construct, like in linear optics, to come up with that, to understand the response of the material and tell us mainly what kind of phenomena I expect from this interaction. Do I get new frequencies? What kind of new frequencies? What kind of other interactions? By the way, there are nonlinear effects that do not change frequency. You're aware of that, right? So if we have frequencies changing, clearly that's a proof that I must have a nonlinear interaction somewhere, right? If I get the second harmonic, we're going to learn about that. But you can have nonlinear interaction that doesn't change your frequency. Is that surprising? Can you think of an example? No?
Thermal lensing.
Yeah. Yeah. So you can have, for example, and we're going to see exactly where that term is coming from. You can have a refractive index that changes with the power of your laser or of your light. Okay? The exact same nonlinearity can give you third harmonic generation. It's a third nonlinearity. But the exact same response can give you the same omega that you put in, except the refractive index depends on the intensity. So think about that. If you send a Gaussian beam into your crystal where it's higher intensity, the refractive index could be higher or lower depending on the sign. But let's say it's higher. So you create a lens in your crystal just because you have a gradient, you have radially kind of decreasing refractive index. That's exactly acting like a lens. But the frequency stays the same. Okay? All right. Okay, so we are going to get into all that. Do you know how many third order nonlinear terms you can get out of a crystal? How many different phenomena you get? How many distinct types of interactions you can get?
So it's going to be one for each axis if it's higher radial.
So 3?
At least 3.
Good. Any idea? Okay, that's closer. It's 6 to the power 3, actually, if you count all of them. I'm going to show you where it's coming from, but think about this. 6 to the power 3, that's 216? 18? 16? That's the kind of richness that you expect from nonlinear interaction. Okay, so it's 3 axes times the field and field conjugate, so that's times 2. And because it's third order nonlinearity, you take that to power 3. And that's all the possible combinations you can have. All right, so that's why it's so interesting. So how do we get to the susceptibility? How do we get to the nonlinear response? So this is the Born approximation thing. So we're going to write in that the displacement is the summation of the two in the same way we had the total field as the unscattered, this one, and the scattered part. It breaks down into this. So this is the linear part. This is the nonlinear, all the terms that have x2 in them. And we're going to say that Here we're going to neglect all the things with x2 in them. So again, we neglect the nonlinear part in the driving term. So we say that the nonlinear equation is driven by the linear response. It's exactly this picture that I stretch the spring, and now I'm looking at small displacements around the new stretched part. Okay? So there is no linear response because I'm solving this, but it's not that bad. It's not huge nonlinearity. The nonlinearity is small. Okay? So I don't crack up the power to crazy levels. I get nonlinear effects, but as small perturbation compared to the linear one. Okay. So another way to think of it, for example, if I get second harmonic generation, the power that I get in the second harmonic is always much smaller than my fundamental, what I put in, the single frequency. Okay? So it's a small perturbation. All right. So the equation becomes very simple then, that x2, whatever, the acceleration term, velocity term, and the restoring term of x2, so the nonlinear part, is driven by x1 squared only. So where x1 is the solution of this one. Okay? So if we do that, then how do I solve it? Well, again, I want to put it in the frequency domain. This in the frequency domain gives me the d of omega times x2 of omega. Because I have a x1 squared here, my product becomes a convolution. Right? So I'm trying to use everything that we learned in this semester. So blah, 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 this constant. Then I have e of omega convolve with itself. So x1 is just e of omega over d of omega. Remember, this is the transfer function. So it's a convolution between these two terms. It's an auto-convolution. Okay, so pretty much that's the whole answer. Now, let's suppose, are you with me, guys? It's a lot of equations in here, I'm aware, but I'm trying to explain more or less what it means. So for example, we're talking about second order nonlinearity, the fact that your driving term has x squared in it. You would expect right away that there will be some double frequencies in there, right? We can anticipate that. So I'm trying to use our procedure here. So we went to the frequency domain. This x1, this function of t squared, x1 of t squared, Fourier transform of that gives you a convolution with itself. Yeah? And now let's make it particular. I have a incident field that looks like this. I'm illuminating the nonlinear crystal with two monochromatic fields at different frequencies. Omega 1, omega 2. So it's going to be E1 delta of omega minus omega 1, E1 conjugate delta of omega plus omega 1, okay? So again, I'm writing the real representation of the field. And the same thing for omega 2. You plug them into the convolution here. So you basically have the following. Delta of omega minus omega 1 plus delta of omega plus omega 1 plus delta of omega minus omega 2 plus delta of omega plus omega 2 convolve with itself. So I have 1, 2, 3, 4 terms convolve with the 4 terms. What do you think we're getting? So I have these 4 terms. So different frequencies may have different strengths. Yeah? This is my input. 2 monochromatic fields. What's going to be the output? So I have this crystal that's a chi2 nonlinearity. I put omega 1 in, I put omega 2 in. What am I getting out? This is what we're talking about. Huh? Yes. But I want you to appreciate how I'm thinking about it. So I input minus omega 2, minus omega 1, omega 1, omega 2. I convolve this with itself. Now let's see what we get. Well, I start all the way from here. We get 0, 0, 0. Most of it is going to be 0 until two deltas overlap. Right? Okay, so if I shift this around, omega 2 is going to make it all the way over there with the minus sign. There we go, so hopefully I have a figure. How many terms do I expect? I start with 4. It's exactly what that, probably that's why I picked them. 2 frequencies, yeah. So, 12. Really? I think it's always 2 times this plus 1, plus the DC one, isn't it? We can count them. So 1. Now it depends which one is bigger, right? So let's say 2, 3 is 3, 4. They are not multiple of each other. So 1, 2, 3, 4. 1, 2, 3, 4. It has to be odd. 7. How many do I have here? I have 9. I think 9 is correct. So you check it out. Okay, so most important, let's see. If omega 2 is higher than omega 1, so it's at the outer left part, then when I flip it around, so the omega 2 from here becomes minus omega 2 because I flipped it. So the first encounter will be when the 2 omega 2s overlap. This is minus 2 omega 2. I know I'm going to have plus 2 omega 2. So 2 right there. Then I shift this a little bit more, and this omega 2 overlaps with omega 1. Okay, except that's minus omega 2, this is minus omega 1, all together gives me minus omega 2 minus omega 1, and its complex conjugate. And they have names, by the way, right? So this is a second harmonic generation of omega 2. What is this called? I put 2 frequencies in, I get their sum out. Huh? It's a sum, for God's sake. Difference is the other one. Sum frequency generation. Right? Second harmonic generation of omega 1. And then this is the difference frequency generation. So this is the frequency generation. And I get my DC. What's the deal with that DC? It was a little bit of a controversy when the theorists like Blomberg predicted all these effects. And it was easy to, it didn't take that long to actually get out second harmonic generation. But it took them a little longer to find the DC term. Because that's harder to measure, right? It's always nice when your signal has some kind of a carrier, some kind of frequency on it. So this is really like a DC voltage that you polarize your crystal. 0 frequency. But that too was measured. So this is real. Okay? Okay, So these are all possible combinations of terms in the general case when we input two different frequencies in. Of course, you can go ahead and input more frequencies, you'll get a lot more combinations, right? But this covers all the different phenomena that you can do with a Chi2 crystal. Okay? So we get second harmonic generation, we get the DC, we get some frequency generation and difference frequency generation. So you can imagine what's the usefulness of all these things from a practical point of view. Ooh, what's in here? What does that give us? The fact that I get these type of frequencies out. I start with two frequencies, right? With two monochromatic fields. I pass them through this crystal. And I end up with 9 different terms. Well, divide by 2. So I get 1, 2, 3 different phenomena, let's say. Forget the DC2. So I get second harmonics, sums, and differences. How is that helping me? That's exciting. Yeah, that's very specific. But generally, you can pretty much produce all kinds of frequencies that you want. You produce new sources, new wavelengths. You make tunable sources. Have you heard of optical parametric oscillators? No? They're based on the exact same nonlinearity. I think I have a figure later, hopefully. Okay, I think, I'll talk about them a little bit later, so I take them one by one. But it's basically the opposite of the different frequency generation. So all these terms work in reverse as well. So if I have a crystal and I put omega in it, I can get out omega prime, omega double prime, such that omega double prime minus omega prime equals omega. Actually, no PO, you want the sum. So you can make up the original frequency that you put in by these two, by a summation of the two. It's the exact opposite of this one. So in the first example, we have omega 1, omega 2, and I get their sum out. Okay, but it also goes backwards. I can put 1 photon in, and it will give me 2 out, such that their frequencies add up. So that's really very interesting because you can generate 2 new frequencies. Usually one is not very useful. The other one is called an idler. But according to the way the crystal is oriented, you can get different values for the new frequencies that come out. So that's why it can become a tunable, really a tunable source that can sweep a lot of different frequencies by you starting with one single laser. Okay, so that's the fundamental for optical parametric oscillator. Okay, so if you just want to understand the frequencies coming out of your crystal, we're kind of done. Once you did that convolution, you can kind of see all the possible combinations. But the harder part is kind of the equivalent to a grating. If you want to just calculate the angle of diffraction at the grating, that's easy, right? Everybody should say yes, very easy. But if you want to know how much power per each diffraction order is, that gets a little more complicated. So this is about telling how much power you get per each frequency. Okay, so that's what we mean by susceptibility. Can you give me a number for that conversion? How much for? So these will be in all these prefactors. This is the strengths. Okay, the prefactors to the delta functions. That tells you how much power you have per each frequency. This equation has the result of second. Okay, so we get all these combinations. Okay, so if you get it, if you Fourier transform this to the time domain, you will get your oscillating frequencies, as you might expect, right? And this tells you these are fixed frequencies, the frequencies that I input, right? So D is a function that we know how it looks like. This tells you precisely how much of each frequency you have coming out, okay? And these are in the time domain. So D, you may wonder, how come this is such a general equation? What if I change my crystal, right? Where is the information, specific information about my specific crystal? And it's in the gamma and the omega naught. So remember, this is something like omega naught squared minus omega squared minus I gamma omega, something like that. This is material property, this is material property. Changing the crystal will change these two little coefficients. Those are the material constants, okay? So if you put I don't know, KDP crystal, Chi2 crystal in there, they will come with their own little parameters. In fact, in practice, you don't look at these microscopic parameters, you look at the bigger one, the Chi's themselves. Okay, but basically this is the solution. So this is the strength. This is everything you need to know. So for linear materials, you have D of omega and you're done. For the nonlinear ones, your chi is something to do with this. So it's as if you have a linear response at 2 omega. So let's look at the second harmonic generation of omega 2, 2 omega 2. So you have as if you have a linear response at 2 omega, and then you have a linear response at omega squared. Yeah? So you take your nonlinear crystal, the strength or the response at the frequency 2 omega at the second harmonic generation is the linear response evaluated at 2 omega plus times the linear response at the fundamental at omega squared. Okay? For the sum, you have the linear response at each frequency, product of them, and then the linear applied at the sum. Basically, second harmonic generation is a particular case of sum frequency generation, right? When omega 1 equals omega 2. Different frequency, same thing. Linear at omega 1, linear at omega 2 times linear at the difference. So this is kind of cool. It means if I know how the response of that material looks in the linear regime, I can predict how it's going to look for any of these combinations, sum, difference, and second harmonic. So all you need to do is to evaluate that linear response at the sum, evaluate at each frequency, product them together. Okay? So this is the harder part, but as you can tell, it's not that hard. It looks a little messy because we have all these many terms in there, but basically it's kind of simple. Okay? So this is the harder part of the nonlinear frequency generation, to tell how much strength, how much power you have for each term. Okay? But even that seems to be actually very manageable. Okay. Here's a typical notation for the nonlinear interaction. This is OP that we talked about earlier. This is the induced polarization. This is a macroscopic thing. By the way, I want you to be clear on this. We're talking here only about the nonlinear effects. The linear part is doing its own business. Doesn't mean it's absent. It's still there. Meaning, if I have my fundamental omega coming into the crystal, that propagates according to the linear response. Maybe it's going to diffract in the crystal, it's going to propagate, phase difference, whatever, as usual. Okay? So that goes through as usual with the linear optics. This comes on top of that. So on top of the fundamental, you have the second harmonic sound frequency. Okay? So that's why here I write P2. But we know the total P, if I want to treat the entire field that goes in the crystal, I have to look at P1 as well. So it's going to be P1 plus P2, potentially plus P3. Okay, but we treat them independently and then we add them up. Okay. So if I put two different frequencies in the system, this is the chi2. So this is just a definition of P2. It's a definition. So it's chi2 epsilon naught is the vacuum thing. And times two different fields, E at omega 1 and E at omega 2. And this notation that you see probably in most of the books is to tell you, it kind of keeps track of all the possible combinations that you can have. Okay? So plus minus omega 1 plus minus omega 2. And in the chi's, you get, this will be the output, and these are the two inputs. Okay, so you get a number of terms out, as we've seen. So altogether about 8 plus the DC. Okay, so how do we get from the displacement x2 to the big induced polarization? As we said earlier, by summing all of them. So this is the induced dipole, little dipole, E times X. This is still microscopic. And then we multiply with how many you have in your crystal. That's the concentration. That could be 10 to the, I don't know, 20. And that gives me the capital P, the induced polarization. Okay? So here's something very interesting. If you have a chi2, that is centrosymmetric. So you have a material that has centrosymmetric symmetry, meaning chi2 of R equals chi2 over minus R. Let's see what happens. Right? So if you reverse it through the origin, the molecule looks the same. Okay, that's what it means. So P2 equals X naught chi2 EE. So first I'm going to write it as chi of minus R okay. Oh, because I have a product between E of R, E of R, I can write that E of minus R, E of minus R, these two will be equal. And because it's centrosymmetric, I can write chi2 as minus R. So altogether, this gives me an induced polarization of P of minus R. Are you with me? So because I have a product between these two, E of R times E of R is the same as E of minus R, E of minus R. And now I'm using the central symmetry, so chi of R equals chi of minus R. So altogether this function now depends on minus R. So this will be P2 of minus R. On the other hand, P2 of minus R will be any, and replacing R with minus R. So P2 of R has to be minus P2 of R, according to the definition from the induced dipole. Where is it? It's up there. Right? So according to the definition, if I change R to minus R, I get the negative sign, so I get minus P2. Sorry, right? So something is messy here. Yeah, right here. So the negative sign, this is P2 of R. So P2 of minus R equals any. I see. So I put the minus inside R. Okay. So this is minus, and I need a minus here. Minus, I think like that. Okay, so one says that R doesn't matter. P of R equals P of minus R. The other one says that P of R should be minus P of R. Altogether, this means that if I have a centrosymmetric molecule, P2 of R should be 0. You cannot have both of them satisfied at the same time, 1 and 2. So this one says P of R, P2 of R, equals P2 of minus R. This is because of the centrosymmetric condition. On the other hand, this is the first condition. The second condition says, according to the definition, P of R should be minus P of minus R. So that means P of R better be 0. Yeah? What does it mean? You cannot have second-order nonlinearities in centrosymmetric molecules, centrosymmetric materials. So that is something interesting. In biology, in fact, you can kind of see this when you do second harmonic imaging of, for example, tissue slices, which is a kind of a good application for it. You will see that what pops up in the second harmonic is mostly anisotropic structures, like filaments. Collagen lights up, which is very long filaments in the tissue. Lights up very well in second harmonic. Centrosymmetric structures, like for example cells, I don't know, nuclei of the cells, is spherical organelles, they don't really light up in second harmonic at all. And it's all because of this very simple condition. Yeah? Are we okay? All right. Okay, second harmonic generation. I put omega 1 in, I put omega in. What I'm going to get out is omega for sure. That doesn't go anywhere. And if I'm lucky, a little bit of 2 omega. It's always that 2 omega is much smaller than omega. That's what allows us to do the perturbation theory. Yeah, so this is the chi2 now. If we use the chi2 definition, which is from here, yeah, this one. This is fundamental to the crystal. This chi2 is the macroscopic quantity. It's the equivalent. It has both refractive index and absorption, both real part and imaginary part in it. So from a measurement point of view, chi2 is what matters. Okay, but what we show here is that actually this P is the same as this one. Once you know the X, the displacement that we computed, you can actually come up with chi. So the formula for chi is actually this. So it has this term in front and then d at 2 omega 1 and d squared at omega 1, as we said earlier. And chi 1, just to refresh, is simply this one. So another way to look at this is to say that chi2 is actually proportional, this is the proportionality constant, proportional to chi1 at 2 omega, and then multiply with chi1 at omega squared. Okay? All right. So you see this picture a lot in most nonlinear optics books. That you can think of this interaction as having a virtual transition in a material, a virtual transition to this virtual level, and then another transition to this another level, and then a decay with 2 omega. So this is borrowing the Jablonski diagram, you know, for quantum mechanical levels, but there is no real level here or any resonant interaction for that particular frequency. This is just a kind of a metaphor, a way of looking at it. These levels are not real. And notice, you don't really need this. I haven't pronounced the word photon yet, and we still were able to get all the correct quantitative results just by using wave theory. So I personally don't really like this, but if you see it in a book, this is what it means. Okay, so just a representation. Okay. So basically, this is telling you everything. It's telling us the frequencies that come out and also how big, how strong they are. Optical rectification is basically the DC part. So notice it's the linear response at omega 1, linear response at minus omega 1, and the linear response at 0. So the linear response in 0 is what? So you remember that d of omega, again, had minus omega squared minus I gamma omega plus omega squared, omega naught squared. So at DC, it means these are 0. So basically, d of 0 will be 1 of omega naught squared. It's a constant. It's a material property. Okay? So it tells you how much DC you're going to get, right? And again, this is real. This is a DC polarization across the crystal that is measurable. Some frequency generation, again, we saw it earlier, the same thing. Your chi2 looks like this, chi1 at the sum, and then times chi1 at each of them. So difference frequency generation, the same thing. So the beauty of this, imagine now that you have the knob to generate really new frequencies. You start with one laser. Instead of buying a bunch of different lasers for the bunch of different frequencies, all you need to do is to actually put the crystal in and actually align it. Basically, all the crystals are anisotropic, which means their response, in this case chi2, will depend on the orientation of the electric field incident, right? This, anything in between will give you different refractive indices. So for example, in the linear anisotropic crystals, we get this splitting, for example, in Wollaston prisms and things like that, because different polarizations will see different refractive indices. Just one second. So imagine if the same thing happens here, basically your chi2 changes with orientation. So depending how you orient your crystal with respect to your incident light, you vary what comes out. You tune the frequency according to the orientation. And that's kind of a beautiful thing. So you really have a tunable source that works with your one input. Yeah?
What's the difference between birefringent and anisotropic? Well, anisotropic is, opposite of isotropic, so it's not going to be...
What's the difference between anisotropic
and birefringent? Because I thought what you're describing is birefringent.
Yeah, so anisotropy at the molecular scale results in birefringence. Okay? So anisotropy means what?
Isotropic means in every direction, so it's the opposite of every direction, so direction.
So direction dependent response. Yeah? So that means you can have different refractive index for different polarization. Say EX, EY, different components of the electric field. So two different refractive index means birefringence. Okay, so if you want, birefringence is the result of anisotropy. So the difference between glass and crystal is glass is isotropic. The molecules are not organized. They don't have long distance correlations spatially. They are not arranged in a certain way along certain directions. While the crystals are, right? They have periodicities and so on. They're in a nice lattice. Okay, so that's what allows you to actually tune the Chi2. The light sees different Chi2s with respect to different orientations. You can imagine that, right? So that means your frequencies coming out will also change as you adjust your crystal. Okay. This is the parametric generation. So this is what I was mentioning earlier. If you start with omega 1, what you'll get out is something that will make back your frequencies that you put in, okay? So I think I was going back between plus and minus. It has to be a plus. So what you get out is omega 2, omega 3, where these two have to add up to your original frequency. So this is what you actually can buy nowadays. It's a commercial thing that you can buy. You have a crystal, you can rotate it, you can put the frequency in omega 1, omega 2, and you get out omega 2, omega 3, and they are adjustable. Usually this is we don't use most of the time. It's called an idler. Okay, so if you rotate your crystal, you are able to adjust what comes out of your as new frequencies. Okay, that's why we call it parametric generation. And then you can amplify it. So it's OPA, optical parametric amplification, and so on. Okay, so this is not going to make you experts in nonlinear optics. My goal with these sections was to give you kind of an idea of how you can use the same formalism we use so far with the frequency domain calculation to actually get started on nonlinear optics. And I think very quickly in a lecture or so we're able to understand all the Chi2 effects that may happen. And actually we came up with formulas for all the strength, all their how strong each term will be. So I think that's not bad. Do you have any questions?
You still have to get the forms. They locked me out. No.
Yeah?
It's on this floor, so it's not.
On this floor?
Yeah, it's on the corner, so you can go get it. I tried my iCard. I had to ask someone to go.
Ah, so I have, okay. Okay, we'll have the forms next time. Any questions about Chi2? So what I mean by not being experts in nonlinear optics, if you want to do an experiment, you will need to read a lot more if you want to put this in practice. But I think the principle should be very clear. What the origin is, why they happen, is because of the magnetic field no longer, the magnetic force no longer being negligible. Okay, third order susceptibility, as you might expect, means that the nonlinear force here is actually of third order in displacement. Okay, everything, the procedure we establish will work the same way. It gets a little messier, because you'll have to power 3 now, you have many more terms. Well, let's take a look at it. So again, I'm going to make my total displacement at x as x1 plus x3. I'm going to neglect all the x3s in the driving force like before. So x1 plus x3 cube here. When I expand this in cube, I'm going to get 8 terms. I'm going to neglect all of them except x1 to power 3. All the others will have some kind of x3 in them. Okay? Again, it's the Born approximation type thing that we're doing. So what it means, again, is that first of all, my x1 stays the same as usual. This is my linear response, E of omega over d of omega. So 1 over d of omega is my transfer function. And then wait. So that thing will come in here, okay? So we take the Fourier transform of that. Okay, so we're still in the time domain, so this is the equation there. This is the solution for x1. Oh, I see, so I put it in time domain for some reason. All right. Okay, so this is x1 in the time domain, so I'm putting all these omega 1, omega 2, omega 3 in the time domain. They will give you e to the minus I omega nt plus complex conjugate. And the driving term of my nonlinear response will be x1 cubed. So I'm going to have this cubed here. So you get a mess of a triple sum over all those terms with possible combination on the signs on each. Okay? All right, it's very hard to see anything. Let's see, maybe it gets better later. Let's look at the polarization for now. We'll come back to that. So, as usual, the induced polarization, third order, will be the concentration times the induced dipole. Okay, E times x3, that's the nonlinear induced dipole. And all I need to do is to plug the x3 in here. So I have P3 equals now the double sum. Chi is ijkl. The output is omega q. Omega m, omega n, omega p is the input. Are you following? And the product of 3 different electric fields, okay? So in the most general case, you can have different components, x, y, z, for the electric field, right? And this tensor, the chi2 before was only ijkl, so third rank, because what it does, it says, if I input my electric field along J, another one along K, and another one along L, chi tells me what will be the component of the induced polarization along the final one. No, along the first one, I. Right? So chi I will tell you the polarization along I. If I apply electric fields along J, K, and L. That's what tensors do. Okay? Yeah, forget about the degeneracy factor. Okay, long story short, we get something that looks qualitatively the same as before. So you have chi for the new frequency omega q when you input omega m and p. You have this constant, and then you have the product of the 4 linear terms evaluated at the individual frequencies, okay? Where d of omega is my usual. You can also write it as chi3 being the product of the linear chi's at each different frequencies, which is what we did before, okay? So this is all very general. We didn't particularize in terms of harmonics or anything. This could give you altogether 200, what is 6 to the power 3? 216? Some of them are redundant, but okay. Okay, so let's look at the most common ones. I put omega in. So this could be degenerated. It doesn't have to be electric field along X at frequency omega and then another one along Y and another one along Z. It could be just one beam, right? That comes in at frequency omega, comes out at frequency 3 omega. This tells you the strength of the interaction, this whole thing. So it's basically the linear, denominate that linear response at the 3 omega, and then multiply with the linear response at omega cubed. It's exactly what we got for second harmonic, except this was 2 omega and this was power 2. So you can write it again as chi1 as 3 omega, chi1 at omega, everything cubed. You can write this picture if you want as virtual levels. Okay, so let me ask you this. Why would third harmonic generation be any useful? For example, for imaging.
You get wavelengths at higher frequencies, so you can. So that means shorter wavelengths and higher resolution.
True. That is true. But the excitation wavelength, so the opposite is, the other side of the story is that the excitation is at lower wavelengths, longer wavelengths, lower frequencies, longer wavelengths, which means you can penetrate deeper in the tissue. So you can use the excitation light in infrared, which has lower scattering, you can get deeper in the tissue, and then generate third harmonic generation, which will have the benefits of the higher resolution and so on. So actually, this is the subject of a Nature Photonics paper recently, I'm not sure, 2014 maybe. So this is from Cornell, Chris Shu's lab. So check that out if you want. So they used third harmonic generation to do brain imaging, deep brain imaging in, I think in mice or rats, I don't remember. And this was the idea. Okay. What else can we get? 2-photon absorption. Let's see how that works. So it's all in the combination of these frequencies. You see, if I have one wave interacting with the conjugate of itself, instead of third harmonic generation, when you add all these up, these two give you a DC, you end up with the same frequency. Okay? There is no frequency change. But you get something very interesting. You get that, first of all, in the denominator here, you get the wait. This cannot be squared. That has to be cubed. Yeah. So remember, because d of omega is omega squared minus omega squared minus I gamma omega, d of minus omega is actually d conjugate of omega. You see it? Because the linear term in omega is actually the imaginary part of this thing. So when I put minus omega here, this becomes d conjugate. So that means when I do d omega, d minus omega, I get magnitude of d omega squared. And then this something is wrong here. Okay, I'll fix this myself. There's something wrong in here. But what's important is that when you look at the real and imaginary parts, so try to break this down. You have the real part, and the response is at omega. So what's the real part usually? The refractive index. And you also get the imaginary part. Okay, so I can write it like this. What is the imaginary part? Attenuation, absorption. So, when we were talking earlier about the lensing, this is the real part. It's a nonlinear effect that changes the real part of the refractive index. Right? So, your refractive index depends on power. You can actually focus the light with nonlinearity, actually, or diverge it, or whatever. But there is the imaginary part, which is basically absorption. As usual. Except your absorption now depends on the power. So this is 2-photon absorption. And you can think of this like 2-photon refraction if you want, but you don't have to. So this gives rise to self-phase modulation, it's called. Self-phase modulation. So imagine as a beam propagates through a crystal, at the higher intensity point you generate a refractive index profile that follows that intensity. In fact, there is something very interesting you can do with this, and that is to compensate diffraction. So if I have a beam that naturally diffracts like this, but now on top I put a crystal that has the opposite profile, so it's kind of like that. It has a negative nonlinearity, so when I apply power, it's actually reducing the refractive index in the center. Essentially, it makes it equivalent to a negative lens. This will be my refractive index versus intensity. You see? Acts, the crystal itself turns into a negative lens, which compensates. Wait a second, negative will do not good. It has to be positive. So it's diverging this way. I need to focus it down, sorry. I make it positive, okay? So I make a lens basically that looks like this. And then I'm straightening it. So I get the collimated. This is called, this is all Kerr effect, all chi3 is Kerr. This is called spatial soliton. A spatial soliton. Goes solitary, I don't know where it's coming from, but I imagine that's where it's coming from. It goes without diffraction. But you have to adjust your power just right to make that lens. You kind of change the focal length of your crystal by adjusting the power. That's very powerful, right? You get to do that. I think the name comes from that. No, it's way beyond. I think the first soliton was observed with the horses in the carriages in the water. Do you know the story? Somewhere in Europe, they were racing horses in these canals. And at some point, they found this interesting phenomena that they were creating these almost like wakes, like waves, like tsunamis almost by the horses, that will go for a long distance without spreading, without diffraction. I saw actually the picture from, I think, 1800s. So apparently that was the exact same kind of nonlinear effect. I'm not sure the details what will bring the water together, but okay, so what's a temporal soliton then? What can it be?
Something that doesn't change in frequency?
Of pulse in time, right? I mean, natural. So what does the pulse tend to do when you put it in a crystal? Because of dispersion, it's going to spread. Now, you make your diffractive index as a function of intensity. You crank up your power just to the point where they perfectly stay together. You can actually measure this in real time. So make a pulse that never spreads. Of course, it's not very practical to do this for fiber optic communications at the bottom of the ocean, right? Because you need a nonlinear fiber. But this has been demonstrated in lab setting. This is a real thing, okay? So not spreading because of that. Okay. So what's cell phase modulation? With this we're going. It means that as the beam propagates, its own intensity modulates the refractive index, which modulates the phase of the beam, which then modulates the refractive index and modulates the phase of the beam, and so on and so on and so on. So it's a self-imposed modification, right? Because this refractive index depends on the intensity itself. Okay, so you can go both ways. You can make the beam spread much faster than it would in a linear crystal if you have the wrong sign, right? So if you had what I drew earlier, if you had the crystal act as a negative lens and this is already diverging, it's going to make it diverge even faster. If you put the correct sign, you can actually undo that. So you see, this is just a preview of very interesting phenomena that just come out of the nonlinear interaction, okay? So we'll continue next time and maybe we'll discuss the exams, hopefully.